Hey guys, this is Electron Configuration Part 1 using the periodic table. You will have to ignore my dogs. They're laying close to me and snoring throughout this entire video. So I apologize now and I will apologize again at the end. And so before we can actually start that, we need to talk about the different sublevels and how many orbitals are in each one. Before you ever learned this back in junior high, you learned about the Bohr atom. They may not have called it that, they may have called it that, but it was the one where you had a number of protons in the middle of the atom, and then you'd put 2 electrons in the first ring, and then you could put 8 electrons in the second ring. And they never really quite explained why you could put 8 in the second ring and why you could put 2 in the first ring. But that's just what they told you to do. Well, the first ring is where n is equal to 1, and the second ring is where n is equal to 2. And n is called the principal quantum number. It's just the energy level. Alright, so about the sublevels, we have an S sublevel. The S sublevel has 1 orbital in it, and so if each orbital can hold 2 electrons per orbital, then there would be 2 electrons in the S sublevel. And then we have a P sublevel, and the P sublevel has 3 orbitals in it, and so there would be 6 electrons there. The D sublevel has 5 orbitals, and there are 10 electrons total there, and then the F has 7 orbitals, and so there's 14 electrons there. Alright, so we have S, P, D, F, and they increase by the number of orbitals by odd numbers, 1, 3, 5, and 7, and you multiply those by 2 to get how many electrons can go in each one of those. Alright, so what does that have to do with n? Well, when n is equal to 1, there can only be an s orbital. When n is equal to 2, there's an s and a p orbital. When n is equal to 3, there's an s, a p, and a d orbital. And when n is equal to 4, we have an s, a p, a d, and an f orbital. When n is equal to 5, an s, a p, a d, and an f, and so on and so forth. So, as you can see, by looking back at this Bohr atom over here, the first ring where n is equal to 1 is just the s orbital, because the s orbital can only hold 2 electrons. Let me see if I can get this back down here like this, where we can see everything. Alright, so, and then when n is equal to 2, right here, we have an s and a p, and so s and p have 2 and 6, so that's 8 electrons. And so that's why you could only put 8 in the third energy level. In the second energy level, I'm sorry. In the third energy level, we have an S, a P, and a D. And so you could get 2 plus 6 is 8 plus 10. You could get 18 electrons in the third energy level, and so on and so forth. So this is where it all starts. Now, the electron configuration is a series of numbers and letters that represent where each electron resides in the atom. So if we go over here to this periodic table, it's completely blank. There's no elements on it. I just wanted to be able to write on here what each area is used for. And so this first pink area, along with helium, all the way over here, is called the S block. And if you remember, the S sublevel has one orbital and it can hold 2 electrons. So that's the number of electrons it can hold, and this is the number of orbitals it has. So that's why this one right here is called the S orbital, the S block, sorry. And so it has it's 2 elements wide. Now, the P block is over here, and it is 6 elements wide because the P sublevel is 3 orbitals, and so it can hold 6 electrons. And so it's 1, 2, 3, 4, 5, 6 elements wide. Now, the D sublevel can hold 5 orbitals, or is 5 orbitals, and can hold 10 electrons. And so the middle green part is the D block because it's 10 elements wide. And then last but not least, we have the F. And so the F orbital, I need some more room. The F sublevel has 7 orbitals and can hold 14 electrons. So this is F here, it's 14 all the way across. All right? Okay, so if we look at, let's say, hydrogen, which is going to be this first one right here, this one right here, hydrogen. Hydrogen has 1 electron, and so we use the period numbers, which you can't see very well, so I'm going to rewrite them over here. This is 1, 2, 3, 4, 5, 6, and 7. We write the period number down first, and so that's going to be 1, and then the block that we're crossing into is S, and it's the first one in that row, so it's 1s1, and that would be the electron configuration for hydrogen. Now, this number represents N, the energy level. This represents the sublevel or orbital, and that represents the number of electrons. So if we move on to helium, which is going to be right here, we would still start at 1, 1, and it's still part of the S block, S, but it's the second one, 2. So the electron configuration would be 1s2. Now if we go down to lithium, which is right here, we have to start from the beginning because we have to fill the lower level first. When you made the Bohr atom, you had to fill up the first ring before you could get to the second ring. And so we have to do the same thing here. So I've got to push 1 and then S. We're going to go all the way through it, then we're going to fill it all the way up. 1s2. So we've got 1s2. And then we're going to have 2s, but it's only one of them because it's the first one. So it'll be 1s2, 2s1. All right, and next we have beryllium. And we're going to do the same thing. We start from the beginning, 1s2, and then we have 2s2. All right, and so next we have boron. And so we have to start from the beginning again. So we have 1s2, 2s2, right? So 1s2, 2s2. Then we have to cross over to here. So it'd be 2p, because we're in the p block now, 2p1, because it's the first one in the p block. 2p1. And so if we add up the electrons here, we've got 2 plus 2 plus 1, and so that's 5, which is exactly, because this is number 5 here on the periodic table, that's exactly how many electrons boron does have. All right, and so let's do phosphorus next. Nitrogen. Let's do nitrogen. And so we start from the beginning. We'd have 1s2, and then we would have 2s2, and then we would have 2p, right? We're over here in the p's now, 2p, 1, 2, 3. And so it's going to be 2p3. And nitrogen is, in fact, number 7 on the periodic table. So if you take 2 plus 2, that's 4, plus 3 is 7. All right, let's look at sodium. Sodium is Na. And Na has 11 electrons. And so if we start at the beginning, we have 1s2, and then next we would have 2s2, and then after that we would have 2p6, because it has to go all the way through it, 2p6, and then we would have 3s1. All right, so let's try one more, and I'm going to write it down here on the bottom. Let's do chlorine. Chlorine has 17 electrons. And so if we start at the very beginning, we'll have 1s2, and then we would have 2s2, and then we would have 2p6, and next we would have 3s2, and then last we would have 3p, oops, 1, 2, 3, 4, 5, because chlorine is right here. Let me write that on there. And so it'd be 3p5. And if you add it up, all of the exponents right here, so 2 plus 2 plus 6 is 10, plus 2 is 12, plus 5 is 17. And so that's all of the electrons in chlorine. Now the first ring has 2 electrons in it, and the second ring has 8 electrons in it, and then the outer ring, the valence shell, has 7. And so valence is the outer ring. All right. Okay, so let's look at this a little differently. On the next slide, we're going to see some rules. If you do not have these rules in your notes, or you need to look at them more closely, make sure that you pause the video and record them down somewhere. All right, so the first one is the Aufbau Principle, and the Aufbau Principle states that the orbital with the lowest energy must be filled first. The second rule is Hund's rule. As electrons enter orbitals of equal energy, which they are called degenerate orbitals, it's an important term, they must spread apart and have the same spin. Then they can pair up. And I know this doesn't make much sense. It will make more sense when we do some more examples. The next one is Pauli exclusion principle. An orbital can contain a maximum of 2 electrons, and those 2 electrons must have opposing spins. All right, so on the next slide I have a periodic table so that we can use it, but we're going to be applying these rules. So if you don't have these rules written down where you can glance at them when I refer back to them, it's going to make it a little more confusing. So I would really try to have these written down somewhere. Okay, so this is just a periodic table so that we can see all the elements on it, but I did block off the S, the P, the D, and the F blocks so that it makes it easier for us when we're doing the electron configurations. Okay, so the first element that I want to take a look at and try is going to be calcium. Looking for a color to write in that's going to stick out, that won't look like everything else. All right, so we're going to do this one first, calcium. And so it has 20 total electrons in it. And so we have to start from the beginning, right? So it's going to be 1s2, and then we'll have 2s2, and then we'll go to 2p6, and then 3s2, and then we'll have 3p6, right? 3p6 all the way through. And when we're done with that, over here, we have to go down to 4s2, and that gets us to calcium. All right, so this type of electron configuration is unabbreviated. I've also seen it been referred to as ground state or longhand. So we're going to look at a couple of different other types of electron configuration, or different ways to write it, and the first one is called orbital notation. And so orbital notation shows all the orbitals, and what you do is you draw a line that represents every single orbital. So a line like that represents the orbital, and so this is going to be the 1s orbital. And then we'll have a 2s orbital, and then a 2p sublevel that has the 3 orbitals in it, because p's have 3 orbitals. And then we have the 3s, the 3p, and the 4s. And so in each of these orbitals we have to put in the electrons. And the electrons are going to go in together, but they have to have opposite spins. And when they enter in orbitals that are degenerate or have the same amount of energy, so like these, degenerate orbitals, they spread apart and they spin the same way, and then they go back and pair up. And so each one of these arrows represents an electron. And so there's all 20 of calcium's electrons. And so now if we go back and we look at a different element, you can see how when we split these up, it makes a big difference. And so referring back to the rules, the reason they have to have opposite spins is because of the Pauli exclusion principle that also tells you have to have 2 there. And we have to fill the 1s before the 2s, and that's due to the Aufbau Principle. All right, so now we're going to look at nitrogen. And so nitrogen, I know you can barely see it, it's number 7, so it has 7 electrons in it. First we're going to do the ground state. So just the regular electron configuration. And so nitrogen's electron configuration is going to be 1s2, right? 1s2, 2s2, 2p, 1, 2, 2p3. So real short, real quick, real easy. All right, and so now if we do the ground state, the orbital notation, we're going to draw a 1s orbital, we're going to draw a 2s orbital, and then we're also going to draw a 2p orbital. And so there's 2 electrons in the 1s, one has to spin up, one has to spin down. 2 electrons in the 2s, one has to spin up, one has to spin down. And then there are 3 electrons in the 2p. And so they spread apart as far as they can, and they all spin the same direction. And I like to refer to that as siblings living in a house. If there are enough bedrooms, they're not going to share a room, they're going to have separate bedrooms. But if they have to share a room, because there aren't enough rooms, then they'll pair up if they have to. Okay, so that's nitrogen. Now, the next type of electron configuration that I want to look at is called shorthand. And shorthand or it could be called abbreviated, or noble gas. What we do is we use the noble gas that comes before our element. So I'm going to shrink this down a little bit more. Okay? And the noble gases are going to all be right here. They have to be in that column. You cannot use any element you want. You have to use the noble gases in group 8A or group 18. All right, and so you use the noble gas that comes before your element. So if nitrogen is right here, the noble gas that comes before it is helium. And we're going to put it in brackets. And that's basically saying I've got everything up to helium inside of these brackets. And so you have to start after helium. And so after helium comes 2s2, and then would be 2p3. So if we go back to this page, then we can write the shorthand configuration for calcium. And so if we're doing this for calcium, which noble gas will we use for calcium? We're going to use the one that comes before it, so we're going to use argon. And we're going to put that in brackets, and that's basically saying that the electron configuration for argon, so everything before argon is inside of those brackets, and then we'll go from argon to 4s2. That really demonstrates how beneficial it can be to be able to use the noble gas configuration, because this is way shorter than having to write out this down here or write all of that out. Alright, so let's try one more, but this time I want to use a transition metal, and so I want to do vanadium. Now, one thing that I haven't mentioned yet is what you have to do whenever you write the electron configuration in the d orbital. The d orbitals are very big, and because of that, if you'll remember, when I said if n is 1, we have an s orbital. When n is 2, we have an s and we have a p. When n is 3, there's an s, a p, and a d. And when n is 4, there's an s, a p, a d, and an f, and so on. Well, we just did calcium, and when we did calcium, we went straight from 3p to 4s. And so we never did anything with D. And that's because D is actually, 3D, in a lot of places, is actually further away from the nucleus, and so it's bigger than the 4s. And the Aufbau Principle states that we have to fill the lowest energy level first. So that means that the 3D is this. It's this period, or this part of the period right here. So it's that row. And so all of this is 3D. All of this down here, I need a darker color. Let's see if I can make it just thicker. This will be 4D, this will be 5D, this will be 6D. And the F orbitals basically do the same thing, except they're even bigger than the D orbitals, and so this is going to be 4F, and this is going to be 5F. Now, if I go through and try to do the electron configuration for vanadium, we'll start at the beginning, 1 S2, and then it will be 2 S2, next is 2 P6, and after that will be 3 S2, and then 3 P6, and then 4 S2, and last we'll have 3 D3. Okay, so now we need to do the orbital notation. So there's 1s, and then 2s, and then 2p, 3s, 3p, 4s, and then the d orbital, or the d sublevel, remember, has 5 orbitals in it. So there's 1, 2, 3, 4, 5. So I'm going to put 2 electrons in each orbital that has 2 electrons. So the 1s has 2, the 2s has 2, right? The 2p has 6. So there's 1, 2, 3, 4, 5, 6. The 3s has 2. The 3p has 6. 1, 2, 3, 4, 5, 6. The 4s has 2. And the 3d only has 3 in it. So we're going to spread them apart, and they're going to have the same spin. Now for the easy one is the noble gas configuration. And so if we're going to do the noble gas configuration for vanadium, the noble gas we need to use is argon. So we'll have argon, and what follows argon is 4s2, (3d3). All right. Let's see. I'm going to write this stuff on here again. So this is 3D. That's not very good either. 4D, 5D, 6D, and this is 4F and 5F. So next I want to do, let's see, palladium. All right. And so we start from the beginning, 1s2, 2s2, 2p6, 3s2, 3p6. Next we have 4s2, and then we'll have 3d10, after that we'll have 4p6, we're back to 4 again, right? after 4p6 comes 5s2. And then last, we will have 4d, 1, 2, 3, 4, 5, 6, 7, 8. 4d, 8. Now the orbital notation is going to take a little time and a lot of space. So got a 1s orbital, got a 2s orbital, got a 2p orbital, a 3s, 3p, 4s, 3d, 4p, 5s, and 4d. All right, so just in case you don't remember why we have so many lines for each one, the s has one orbital. It can hold 2 electrons. The p has 3 orbitals, so they can hold 6. The d has 5 orbitals, can hold 10, and the f has 7 orbitals, it can hold 14. And so that's why the p down here has 3 orbitals, and the d has 5. Okay, so now we got to add the electrons in. So I've got 2 here, 2 in this one, 6 in this one, 2 in this one, 6 in this one, 2 here, 10 in this d orbital, and they have to have opposite spins, 4p, 5s2, and 4d8. Now remember, they're going to spread apart as far as they can first. There's 5, and then they'll pair up, 6, 7, and 8. And so I have 2 unpaired electrons in the 4d orbital for palladium. Okay, and then we need to do the shorthand notation. So if we look at palladium right here, the noble gas that comes before it is krypton. So I'm going to just write it right over here, krypton. And then we start after krypton would be 5s2. And then we would have 4d8. All right. I want to talk about some exceptions to these rules. All right. And the first one we're going to look at is the one that affects chromium and molybdenum right here. All right, so chromium's expected, chromium's expected electron configuration, and I'm just going to write the shorthand is going to be argon, 4s2, 3d4. And so this is what you would expect to see. And so we'd have a 4s, and then 1, 2, 3, 4, 5, 3d, 2 electrons here, and 4 electrons here. And since it's expected and I'm having to explain it as an exception, then it must not happen. So what actually happens is one of these electrons comes up here and fills the 3d orbital instead of being where we would expect it to be. And so what you really get is you get argon 4s1 3d5. Okay, and so the same thing is going to happen with molybdenum here, except it will be 5s1 3d5. And the reason for that, there's a little controversy surrounding why it happens, but obviously somehow these two orbitals become degenerate, and they're equal in energy, and so they spread apart as far as they can, or at least that's one of the major arguments. So you need to know them. And then the other group of exceptions that I want you to know is copper, silver, and gold. And so we'll look at copper's electron configuration. I'm going to move this as far over as I can. So copper is also going to be argon, and we'll have 4s2, 3d9. So if this is 4s and this is 3d, we have 2 electrons. And then 9 in the 3d, and the same thing happens. One of these electrons comes up here. And what we end up with is argon 4s1 3d10. So the 4s has only 1 electron in it, and the 3d has 10. So in this case, it almost looks as if, there we go. It almost looks as if the 3d has become lower in energy than the 4s. Alright, so I know that's a lot of information to take in one thing. There's also some interesting stuff that goes on in the f orbitals, but we're not going to get into that much. The best advice I can give you is if you're given an electron configuration, the easiest way to figure out what element it is to add up the electrons. And so if you were to see an electron configuration like this, and you were unsure of which element it was, you would just add them up. Argon has 18, plus 1 is 19, plus 10 is 29, and so you find number 29 on the periodic table, and that would tell you that it was copper. And I think that's pretty much it. If you have any questions, please ask and keep trying. It will all eventually make sense one day. Good luck. Alright, so one thing that I did forget to mention on here that I wanted to say after I went over the exceptions is that the elements in the middle follow the same rules we've been talking about. So manganese is going to be 4s2 3d5. Iron will be 4s2 3d6. The only ones that have those expectations are the ones that I've highlighted here. So don't do that to any other elements in the D block. Alright? Okay. Oh, and I'm sorry that my dogs were snoring the entire time I was recording this.